How do we determine the energy requirements of a proposed factory unit? As it doesn't physically exist yet, we will need to use a calculating tool to give us an estimate of the factory's electrical load. In this video, we will determine the maximum demand of a three-phase factory unit using Appendix C of AS NZS 3000. We will follow the worked example C2.4.2.2 from the appendix. Table C2 and column 3 will be our focal point, as this covers factory units. As you recall from previous maximum demand calculations, various loads are first placed into load groups. Once all loads have been allocated to the correct load group, the calculation can begin. In this calculation, some specialised loads not encountered in previous examples are presented. We will spend a little time on each of these to clarify loading allocations. Load group B3 is for socket outlets exceeding 10 amps in buildings or portions of buildings with no installed permanent heating or cooling equipment. Load allocation from Table C2, column 3, allows 100% loading of the highest rated outlet and 75% of the full current of the remaining sockets in that group. Load group H of Table C2 covers welding machines. A definition of loading for arc and resistance welders is covered by section C 2.5.2 and will be explained as a load group allocation for these machines is made. As previously stated, this example is for a three-phase factory unit. It is evident from the load group list that the factory consists of both heated and cooled and non-heated and non-cooled areas, as both socket outlet load groups B1 and B2 are present. This installation would typically represent an office and workshop area within the same building. Now, let's start looking at our load groups and load allocations, adding calculated values as we progress. In load group A, we have 30 double fluorescent fittings. The allocation here is connected load. It can be assumed that when operating, all factory lights will be on together and no percentage of load value is applied here. According to the calculation, each fitting draws 0.42 amps from the supply. In this example, the lighting load is evenly spread between red and blue phases, with 15 fittings on each of the phases, contributing 6.3 amps. Turning to load group B1, we have 10 outlets in total, and once again, they will be split over two phases. The calculation is 1000 watts for the first and 750 watts for each of the remainder, with 5 outlets in each of two phases. Current loading equals 17.39 amps. Load group B2 contains 4 double outlets. The first is again 1000 watts, with 100 watts allocated to each of the remaining outlets. The total load is 1700 watts, which gives a current load of 7.39 amps. This group is placed in the white phase. Load group B3 contains one 15 amp and one 20 amp outlet. The 15 amp outlet will be placed in the red phase and the 20 amp outlet in the white phase. Full load current is applied to each, as they are the only B3 load in their phase. The single phase air conditioner falls into load group C. The 4000 watt rating is its energy draw, not its output heat capacity. This can be confusing, as modern air conditioners are marketed using their output heat capacity stated in watts. As there is only one unit, a fully connected load is used, and 17.39 amps is placed in the blue phase. Both the rolling machine and the lathe use three-phase motors. These fall into load group D, with full load rating of the 5.5 kilowatt rolling machine and 75% of the 4 kilowatt lathe. This gives 10.4 and 6.2 amps per phase for these units. The 3600 watt single phase hot water system is placed in load group G and is assigned full load current with 15.65 amps in the red phase. Our first load considered in load group H is two 3-phase arc welders. C2.4.2.2 B1 requires that for the first two large arc welder machines, 100% of rated primary current is used for the purpose of maximum demand. This means that both machines will contribute 10 amps to each phase as they're loading in this example. We now turn to our two manually operated spot welders. These devices are two-phase machines and are classified as resistance welding machines. The 30 kVA machine has a primary current of 50 amps, with the allowed maximum demand being 50% of the primary current. So 25 amps is applied to the white and blue phases. This value is derived from C2.5.2.3 A1. The 15 kVA spot welder has a duty cycle of 20% and a line current of 25 amps. From C2.5.2.3 A2, we first apply the multiplier of 0.45 as associated with the 20% duty cycle, giving a current value of 11.25 amps. As this is the second machine in the group, 60% of this value is now used in the maximum demand calculation under subclause B. The current is rounded up to 6.8 amps for the calculation and split between red and white phases. With all loadings now allocated to each phase, we can calculate the highest load phase, which becomes our maximum demand for the installation. In this example, the blue phase has the highest loading, so the maximum demand is 102.68 amps. Now we have seen from example 5 in section C of AS NZS 3000 how to calculate a maximum demand for a factory unit. As an exercise, you could try adjusting single-phase load allocations to more closely balance the total phase currents.